It's our pleasure to welcome Dr. Bhaskar Kamble from Germany. I'll read his bio and then he can start his webinar. Dr. Kamble is an author, theoretical physicist, and data scientist. He obtained his PhD in theoretical condensed matter physics in 2010 from the IIT Kanpur, India. Thereafter, he worked as a researcher for several years at the Ruhr University in Germany and at the Asia Pacific Center for Theoretical Physics in South Korea, specializing in the fields of unconventional superconductivity, quantum phase transitions, and many particle physics. Currently, he works as a data scientist in Berlin in the field of energy analytics. He has a deep interest in the history of mathematics in the Hindu civilization and in Hindu philosophy. He is the author of the best-selling book, The Imperishable Seed: How Hindu Mathematics Changed the World and Why This History Was Erased, 2022. Welcome, Dr. Kamble.
Thank you so much for the kind introduction, and I'm really honored to be invited to this webinar. So I'll be talking about, as you know from the title, the historiography of the Pythagoras theorem and the Sulbasutras. So it is not a history, but it's rather a history of how the history of the Pythagoras theorem and the Sulbasutras was created. So I have actually, this is one of the outgrowths of the research I did for my book, The Imperishable Seed: How Hindu Mathematics Changed the World and Why This History Was Erased. So after publishing the book, I also kept researching on the topic and came across more and more new information, and which I collected in a series of articles, and part of which I will present in this talk. So in this talk, the motivation, I just have a question, sorry, before I proceed. How long is the talk supposed to be? Is it 40 minutes?
You have 40 minutes, 40 to 45 minutes, and the 15 minutes are for any question and answers.
Okay, great. All right. So the motivation of this talk, is basically because when people speak about the Pythagoras theorem, people implicitly believe, that it was discovered and proved by Pythagoras. Why otherwise would it be called the Pythagoras theorem? And some people who are a little bit more knowledgeable, they will be aware that, okay, it has something to do with the Babylonian civilization, which came before Pythagoras around 1700 BCE, whereas Pythagoras was, if I remember correctly, around 500 BCE. So but what many of these knowledgeable people also have no idea about is the Sulbasutras, in the sense that, if you ask them, have you heard about the Sulbasutras, the question will be obviously totally mystified expression you will get from them, most of the people, maybe not from, at least in the West. So this was some of the things that made me research this topic further. Why does this ignorance about the Sulbasutras exists in this world, and why is the discourse dominated so much by Babylonian mathematics? Why did it turn out like that? So the tracing the history of this phenomenon, and finally, and of course, when the whole discourse is dominated by Babylonian civilization, obviously, the Sulbasutras get totally pushed out of the picture. They become like a footnote in the history. So in the process, I also want to show, the actual importance of the Sulbasutras, how it has been forgotten, these are some of the aspects for the talk. And as I mentioned, I have written a series of articles on this topic on my blog, Substack blog. So the Sulbasutras and the Pythagoras theorem, I'll be basically, giving content from this article in this talk. And I've also written more detailed information about the square root of 2, how it's treated within Babylonian mathematics in the Sulbasutras, part of which also I will talk in this presentation. And finally, there is a rather technical article on how the Sulbasutra authors they came up with the approximation for square root of 2, and the reconstruction by various other authors later on, which also I will address a little bit in this talk. So Sulbasutras, I think most of us are familiar with what they are. They are a set of mathematical geometric rules for creating Vedic altars for Vedic rituals. And sutra is a short phrase which is concise and which can be easily memorized. And sulba means literally in Sanskrit rope. So this sutras for the rope. That's because the rope was used for measuring the lengths of various altars and so on. So there are different kinds of rules given here, and also there are different reasons why they are important. For example, you need to have very specific rules for the Vedic altars. The direction in which they face, they should be properly, that is properly specified, and that should be properly done. And then the various directions, east, west, north, south. So for example, in the Katyayana Sulbasutra, there is one of the oldest methods of finding out the directions, the so-called circle method, from the movement of the sun. Then various geometric rules for finding out the if you have an altar of a given shape, you want another altar of a different shape but with the same area, something like that. Or you need to have altars in certain ratios of areas. These kind of aspects are contained in the Sulbasutras, and in the process there is a lot of there is a wealth of information, mathematical rules in the Sulbasutras. And there are various authors of the Sulbasutras. Bodhayana, Apastamba, and Katyayana are the most well known. They are parts of the Vedas, as I have written here, and they can be considered to be Vedic mathematics in the true sense, because they are part of the the Vedic text and to the Vedic era. And the estimates, the official, or let's say the commonly accepted estimates for the Sulbasutras are 800 BCE. But as we will see, they could be much older. So this is something we have to also keep in mind. And moreover, the texts state that this is not new information, but that this is information that was known to the earlier Vedic seers, which is being repeated. So so the two aspects that I will be discussing about here in the context of the Sulbasutras, the so-called Pythagoras theorem and the approximation for the square root of 2, as I spoke about. So so Pythagoras lived, I think it was around 500 BCE, and the result attributed to him, the so-called Pythagoras theorem, actually the first ever explicit statement of it is found in the Sulbasutras, given in the Bodhayana and the Apastamba Sulbasutras here, in this Sanskrit verse here. And they give it in terms of a rectangle. So if you have a diagonal of a rectangle, the square of this this diagonal is equal to the area of the diagonal. Square of the diagonal is equal to the sum of the squares of the other two sides. So this is what it says, and there are actually there is a very interesting application of this also in the Sulbasutras. So suppose you have two squares, one big square of side A and one smaller square of side B. And how do you want to find out a new square whose area is equal to the sum of the areas of these two squares? So this is the sutra which is given here on the rule for constructing this, and this essentially means that the way to proceed is that you mark a side here of length b that is equal to this side of this square, and then you take the square formed by this diagonal. So like here, and then if you then it turns out that the area of this is equal to a square plus b square, and this you can see immediately, because C is the diagonal of this rectangle, or the hypotenuse of this right angle triangle. So by the application of this so-called Pythagoras theorem, you can see that c square is equal to a square plus b square. But what is very interesting is that this actually this implies a proof of the so-called Pythagoras theorem, because right now I just said that, okay, we know the Pythagoras theorem, and so this is equal to the sum of the areas. But actually, if you look at the construction, it turns out that the construction, it implies the proof of this so-called Pythagoras theorem. So if you look at this picture here, which I have again shown in color, and I will make the diagonal of this rectangle here. So you have again this square here, and I will make these two triangles red in color. So just let me do that. So this is red. So going back again, so the area, total area is a square plus b square. Now I make these two triangles red, and I just shift these two triangles to the places shown here. So I have just moved the pieces a little bit. So the area remains the same, a square plus b square, but that is also equal to the area of this square, which is equal to c. So that immediately we can see that a square is equal plus b square is equal to c square. So obviously they don't say that this is how the result is to be proven, because they are not, the Sulbasutras are not mathematical texts. They are sutras for Vedic construction of Vedic altars. But the fact that this this sutra implies a proof of the result was noted by many scholars across the ages. Konrad Müller was a German mathematician in 1929. He wrote about this in his article. The screenshot of this I've given here, exactly the same thing which we saw just now. And this was also pointed out by many other historians of mathematics, Vibhuti Bhushan Datta being one of the foremost. And in recent years, AK Datta, Amartya Kumar Datta has summarized the different proofs, the different works of the authors, scholars in this regard in his article on the Bhavana magazine here, which is a really well worth reading article. So this is the name, the little known fact about the Sulbasutras, that not just that they contain the result, the statement of the result, but also there is a implied proof of the result in their constructions. And when you come to the evidence, for that Pythagoras, what is the evidence that Pythagoras was the one who discovered this result or proved this result? There's actually none. So this is stated explicitly by, for example, Thomas Heath in his book, and Thomas Heath is one of the biggest scholars of Greek mathematics. And this was stated by him that there is no evidence that it was discovered by Pythagoras. I don't have the screenshot where he says this, but it's there in his book itself, A History of Greek Mathematics. And there were also other historians like Hermann Hankel, who also gave, well-reasoned arguments why Pythagoras cannot be associated with this result. And as you can see here on this screenshot. And there were also, like, there was Proclus, was a mathematician in in the 5th century CE in Europe. And he had written a commentary to Euclid's Elements, and there he very carefully, he did not basically state that Pythagoras was the discoverer of this result, but more like, it was attributed to Pythagoras, which means that he does not have any evidence also, which is also again pointed out here by Thomas Heath and again by Hermann Hankel in their works on this topic. So now that this is really very interesting that there is no evidence that Pythagoras was the one who discovered this, but how this became a the almost the absolute truth in the history of mathematics. So this we will try to see how this turned out, and for that we need to know how the Sulbasutras were introduced to the West, and from there we can trace the history. So they were introduced by this Indologist called Georg Thibaut, and in 1875 in the Journal of the Asiatic Society of Bengal, he translated parts of the different Sulbasutras, and there it becomes like he also, the statement of the so-called Pythagoras theorem is also given there, and a lot of other mathematical rules are given there. So it became very clear that Thibaut did not assign any dates to the Sulbasutras, but he made it clear that this is original Indian tradition, mathematical tradition, and it has got nothing to do with the Greek tradition. So this was the thing he said, and this was obviously a big a blow for the accepted narrative of mathematics, in which at that time, in which mathematics comes exclusively from Greece, and the Greeks are the originators of mathematics. So this was the prevailing narrative, which still is to a great extent. And suddenly the Europeans are forced to face the possibility that the Greeks are no longer the inventors of plane trigonometry. So this was actually even pointed out by Abraham Seidenberg in his 1978 article, The Origin of Mathematics, that Thibaut did not formulate the obvious conclusion that the Greeks were not the inventors of plane geometry, rather it was the Indians. At least this was the message that the Greek scholars saw in Thibaut's paper, and they didn't like it. If the Indians invented plane geometry, what was to become of Greek genius or the Greek miracle? So this was the. So how was the reaction to this? How did the European scholars, historians of mathematics, they react to this? Well, the most prominent reaction came from Moritz Cantor. He was the most influential historian of mathematics, and his works, starting from the second half of the 1870s, they had the great sway on the history of mathematics, or the narrative of the history of mathematics. So before that, as I had shown you, some of the snapshots from Hermann Hankel's book. Hankel was, before Moritz Cantor, and he published his book, I think, in 1871 or so. Actually, he did not publish his book. Hermann Henkel died before his book was published, but after his death, his father took over the task of publishing his book, and so that is how his book came out. And so he did not live to see the introduction of the Sulbasutras to the West by Thibaut, and obviously not the reaction as well by Cantor and subsequent mathematicians. So after 1875, that the Sulbasutras were introduced by Thibaut. In 1877, Moritz Cantor wrote the first article in this Greco-Indische Studien in this journal, and in this he assigns a date of 140 CE to the Sulbasutras, and he also says that this was also the date of Panini in the Sulbasutra in this article. Panini, of course, we know that he was much older, around 500 BC is the accepted date, and with this date, it is easy to conclude that the Sulbasutras, they come from Greek geometry. In particular, he claimed that Heron was the Greek mathematician whose works, on whose works the Sulbasutras were based. So so he 140 CE, as I said, was the date that he stated, and right. And then he also implies that other mathematicians like Bhaskara and Brahmagupta and Aryabhata, they also were like were influenced by the works of the Greeks, and so obviously like Indian mathematics becomes just a derivative of Greek mathematics according to him. And this is what he also repeated in his very influential book, Lectures on the History of Mathematics, here, which I've given here, and what he says to the Pythagoras theorem, well, the Pythagoras theorem is due to Pythagoras himself. So, and that he does not have, and obviously it cannot have been derived from the Indian geometry, because Indian geometry was 140 CE, and here Cantor is very careful not to imply any Egyptian or Babylonian influences on Pythagoras. So even though it was known that Pythagoras was like that these civilizations, they predated Pythagoras. So right, and then so here is a statement from him. Some of the things which particularly belong to the history of mathematics we will not refrain from attributing to Pythagoras. Among them is the Pythagoras theorem, which we want to preserve under all circumstances. So I have not actually given you the details, but at that time in his books he also makes some mention about this, right angle triangle 3, 4, 5, and how the Egyptians were probably familiar with this triangle, and then he makes the whole case that Pythagoras may have got this triangle 3, 4, 5 from Egypt, and then he noticed that 3 square plus 4 square equal to 5 square, and then from this he made the generalization for all right angle triangles. So this is the sort of story he puts, but there is actually he may have got it from Egypt. So it is very carefully he preserves it as a discovery of Pythagoras. So so right, so here I have also so the same thing you can see here, which I had stated earlier. So this was the the main picture which continued. But in 1884, the Indologist Leopold von Schroeder, he wrote a very important article called Pythagoras and the Indians. So in this article, he discusses the whole philosophy of Pythagoras, because Pythagoras was known more for his philosophy than his mathematics. So and there he traces the similarities between this philosophy of Pythagoras and the Hindu and Buddhist thoughts, religious traditions, and also the mathematics of Pythagoras and the Sulbasutras. And then he comes to the conclusion that that Pythagoras must have obtained his mathematical results from the Sulbasutras, from the Indian tradition. So and this also in that time it also makes sense, because the Sulbasutras, they predated Pythagoras by several centuries, and if the philosophical doctrines of Pythagoras are similar to that of the the Vedic doctrines, like rebirth, the cycle of birth and death, and finally ending in enlightenment or moksha, which also was what the Pythagoras said. If this is to be found in the Vedas, and if the Vedic texts also contain the mathematical theorem known as the Pythagoras theorem, then then it obviously it's a logical consequence that he must have got that result also from the Indian sources. And here he dismisses the dates of Cantor of 140 CE as absolutely impossible, and he's very clear that that they predated Pythagoras. So yeah, this is a very interesting article. It's a long article, 70-80 pages. So he talks about Sankhya philosophy and the mystical quality of numbers of Pythagoras and so on. So yeah, but it's in German, and I have translated parts of it into English. So here you have those English translations. We cannot doubt the conclusion that the Pythagorean theorem, known in the old priestly geometry of the Indians, uh, yeah, exactly, Pythagoras had established these in the Greek-Italian world, right? Right. So, and then we are inexorably forced to the conclusion that Pythagoras took the teachings of the five elements, just like his theory of transmigration of the soul, his mathematical theorems, from the Indians and brought it to Greece. So, it's very interesting that in after this article was in 1884. In 1894, Moritz Cantor published his next edition of the lectures on the history of mathematics. So, in this, he makes no reference to the work of Schroeder. Okay, he just as if it, like, in modern language we would call it as ghosting. So he basically makes no reference to this work of Pythagoras, and he repeats his claims of Pythagoras being the sole discoverer of the so-called Pythagoras theorem, with maybe some influence from Egypt. And this is very interesting because later on, Cantor also writes in one of his articles that Schroeder sent him a copy of his article, but he found it very improbable that what he said could have been true, so he did not refer to it. And we come back to Georg Thibaut, who in 1875 had introduced the Sulbasutras to the Western world. So in 1899, Thibaut wrote a work in German, which basically dealt with Indian mathematics and astronomy. So here he, by this time the whole narrative is that the Pythagoras theorem is from Pythagoras, and the Sulbasutras come from the Greek mathematical tradition, especially from Heron, and the date is 140 CE. So here he is very much intimidated by Cantor's reputation, as the text will show, and he was still honest enough, or at least he had the he at least admitted that the dates proposed by Cantor were wrong, and that the Sulbasutras predated Greek geometry. So, but he says that basically, so and maybe I just go to the yeah. So he makes maybe I just show you this part. Yeah, so he balances it by saying that there is nothing striking in the independent development of a limited amount of practical knowledge by two different peoples. So this limited amount of practical knowledge being the Sulbasutras, the mathematical knowledge of the Sulbasutras, and then the Greek mathematics. So this is the sort of effect that the reputation of Cantor has had on Thibaut by this time. Then in 1901, the German mathematician Indologist Albert Burke, he brought out a German translation of the Apastamba Sulbasutra. In effect, the content was very similar to the content that was given by Thibaut, but there were some more details and things like that. So this was that, and in 1901, and in 1905, Moritz Cantor apparently had a change of heart after reading this translation by Burke. So he becomes convinced that the Indian Sulbasutras, they predate Pythagoras. So and then yeah, and then, but now instead of admitting that or even conceding the possibility that the Pythagoras theorem could have come from the Sulbasutras, from the Indian sources, he suddenly turns to Egypt as the source of the result. And then he suddenly discovers the different the wonders of Egypt, the Egyptian civilization, and how Pythagoras could have obtained from it. So yeah, so right, and then so he persists with his view of the so-called Pythagoras theorem being from Pythagoras and maybe from to some extent from Egypt, but the Indian connection is totally disregarded, ignored, even though the dates, now he's convinced with the dates. And it's very interesting that if you look at the work of Thomas Heath from 1921, so the way he speaks about the so-called Pythagoras theorem is very interesting. That that there is a that so-called Pythagoras theorem in the Sulbasutras, they were deduced from a certain number of specific cases with integral triangles. There is no general proof, and this kind of things. So you can kind of notice the difference with which Heath treats the Sulbasutras and with which you know, Cantor treats the Greek tradition, and later on, as we will see, how the Babylonian tradition was treated. So I have just given here this statement by Heath to make a comparison with the Babylonian tradition later, as we will now see from this slide onwards. So in the 1920s onwards, starting from the early 1920s, there was a lot of rise in the rise of interest in the history of Babylonian mathematics. So so what we call as Babylonian mathematics actually it comes from the region in the Middle East, and it is in the so-called the Mesopotamian region, and the name Mesopotamia comes from the rivers Euphrates and Tigris, because Meso means between and Potamia means rivers, so between rivers. So this was the civilization which flourished in this part, and Babylonian mathematics refers to the mathematical text, not the texts but the cuneiform scripts of this region, the clay tablets that were found in this region. So yeah. So and then there are, like, so in the 1920s onwards, research on Babylonian mathematics took off due to the work of Otto Neugebauer. So he was very his work on the Babylonian tablets became very influential in the history of mathematics, and we will see how his treatment of Babylonian mathematics compares with the treatment of the Sulbasutras by Heath and by Cantor, etc. So in the 1928 paper, he discusses a length of the diagonal of a rectangle given on a Babylonian tablet, and there he claims that the stated solution is based on this approximation square root of 1 plus x is equal to 1 plus x by 2. And from this he further assumes that this is they knew that this 1 plus x by 2 is like, they knew that the approximation that the diagonal of a rectangle is equal to square root of a square plus b square. Whereas if you read the article, you cannot just conclude that, just because you know this approximation, it follows from this. So there's not enough information from that. So I won't be able to go into details, but you can see the difference between how Babylonian mathematics is treated right from the start. So, and Neugebauer places the Sulbasutras between 800 CE and 200 CE, and he claims that the Babylonian mathematics to be the common origin of the Sulbasutras and the so-called Pythagorean mathematics. So he says in this text that the difficulties which arise from assuming a direct borrowing from the Greeks from India fall away on the assumption of a common origin in Babylonia. So this was he discusses this further in his text in 1945, mathematical cuneiform text. So this was one of the most important texts with respect to Babylonian mathematics. And one of the things he discusses there is a clay tablet which relating to the square root of 2. So this is the famous artifact YBC 7289. So here you see a square picture of a square, and here you see these diagonals, and here you see these numbers 1, 24, 51 and 10 written in the Babylonian script. So so if you since the Babylonian number was in the sexagesimal, it turns out that these numbers are an approximation to the square root of 2. Okay, so we'll just have a look at that later on. So so we come here. As 1, 20, 24, 51 and 10, these 4 numbers we just saw here, they are actually represented in the Babylonian, in the sexagesimal notation as this: 1 plus 24 by 60, 51 by 60 square and 10 by 60 cube. And if you calculate this, it comes out to be equal to this number, which is an extremely accurate approximation to the square root of 2. So and it turns out, like Neugebauer tried to find out how they came to such an accurate approximation. So he claims in his article here, which I just showed here, if you look at here, that they use this specific algorithm for finding out the square root of a number. So this is like, you keep on taking the average of the arithmetic mean of Ri, and so in fact, if at the ith iteration you want the square root of number n, and at the ith iteration Ri is the square root, at the next iteration you take the new value of the square root of half of Ri plus n by Ri. So you will see that, if you keep on doing this, Ri and n by Ri will keep coming closer and closer to each other. So ultimately we'll get R square is, very close to n. It will not be equal to n obviously, but very close to n in case of irrational numbers. So he says that they knew this was the square root of 2 and used this algorithm to find this out. So, and now now this is like, this very, when you look at this square root of 2 given in the Sulbasutras, you have this expression 1 plus 1 by 3 plus 1 by 3 times 4 minus 1 by 3, 434. So, and this is said, and there is a there are many reconstructions by later day authors how they came to this result. So one of them is that, if you have if you have a rectangle with side of 2 and 1, you divide this into two squares, and you rearrange all the parts of this square like this and try to construct a new square from this rectangle. So, and there is one of the sutras which talk about this. And then if the side of this square will be an approximation to the square root of 2, because the area of this square will be, or this region will be, equal to the area of this rectangle, which is equal to 2. So if you do this sort of an arrangement, you get the first three terms of the Sulbasutras: 1 plus 1/3 plus 1 by 3 times 4. And as regards, the other term, the final term, there were other reconstructions. This one was given by Thibaut, so I will not go into this. But the one which is most commonly accepted today is the one given by Vibhuti Bhushan Datta and later extended by David Henderson. So Vibhuti Bhushan Datta, he reconstructed this method, how this was achieved, and Henderson simply extended this method to higher and higher levels. So you have an infinite series representation for the square root of 2. And which becomes more and more accurate. So yeah, so coming back to this, if this value of the Babylonian value was indeed obtained by this method, you have to, I mean, you have to, okay, what I want to say is that, it's the way you obtain this value is independent of the method by which you obtain this. So if you use this method or any other method, it's ultimately going to be independent of the method. It's only when you say that, when you look at the fractional value that this number represents, and if this fraction appears in these iterations somewhere, that you can say that, okay, this was indeed used by the Babylonians. So if you look at this iterative algorithm I pointed out, starting with 3 by 2, then the next number you get is 17 by 12, then the next number you get is 577 by 408, and nowhere you encounter the fraction, this one, which represents the Babylonian value. Very interestingly, if you look at these numbers, 17 by 12, 577 by 408, these 17 by 12 represents the first three terms of the Sulbasutra approximation. 577 by 408 represents the next four terms. And if you look at the other higher order terms, they all follow exactly from this algorithm. So, if you look at the fractions, then it could well be that the Sulbasutra's method is based on this approximation, because, if actually the fractions are there, the exact fractions. I mean, of course, very interestingly, the geometric method is not equivalent to this, this algorithmic method, which was the geometric method proposed by Datta and Singh and extended by Henderson. But the two methods actually turn out to be equivalent, as I have also written in one of my Substack articles, the third one. So this is really one of the interesting things. And if you just make a digression to what he wrote in 1921, he says that the square root of 2 is given as an approximation of square root of 2. But the author does not say anything which suggests that the knowledge was an approximation. The author of the Sulbasutras. This is, of course, false, because they have this term called savisheshaha in the original Sanskrit sutra, which means that it exceeds the actual value of square root of 2. And then this method was used to find out the square root of 3, in an iterative way by the Sulbasutra authors. And he says that this method is also only an approximation. So obviously it has to be an approximation, because it's an irrational number. So remember that in 1921, not much was known about the Babylonian mathematics, only about the Sulbasutras, with the texts which predated Pythagoras, and which contained the explicit statement of the so-called Pythagoras theorem. But you can see the difference with which the Sulbasutras are treated, and the difference with which the Babylonian mathematics are treated. So yeah. So then the final definitive, the phenomenon which occurred was the discovery of the so-called Plimpton 322 clay tablet, and this was like columns of 4 columns of numbers, and which Neugebauer showed that they are integers which satisfy the relation a square plus b square equal to c square, and so he claimed that they knew the so-called Pythagoras theorem. So and then the statements by Neugebauer is that what is called Pythagorean in the Greek tradition had better be called Babylonian, and he says that this is fully confirmed by the texts discussed here in this book on cuneiform scripts. So it was due to this history that the Babylonian mathematics tradition became totally accepted as the precursor of the so-called Pythagoras theorem. And the statements of Neugebauer with respect to the Sulbasutras that they were 800 BCE, they all further served to throw them out of the common narrative of mathematics. So this is the consequences, as I just pointed out. Sulbasutras were removed from any serious discussion on the history of mathematics, and Babylonian mathematics were depicted as the precursor of Greek mathematics and the origin of the Pythagoras theorem. So the Sulbasutras get pushed out of the picture, and yeah. So why is it that there is so much of emphasis on the Babylonian origins of mathematics? Well, there are several. One of the things is that Babylonia is a city which is found mentioned in the Bible, and so by doing this, it becomes more acceptable to the Western trajectory of history to put it in a biblical picture, to put it more in the and to paint Babylonia as the cradle of civilization and those kind of phrases which we know, and obviously in the process, Sulbasutras, we don't hear much about them, and what is also forgotten is that very important facts are forgotten. Like, for example, it's forgotten very often that the Greeks were also they had their own gods. They had their own religious altars. And in fact, in my book, The Imperishable Seed, I have discussed this commonalities between the religious altars of the Greeks and the Vedic altars of the Hindus, and how it becomes a very distinct possibility that that there was at least a common cultural ground between Greece and India, where this mathematics, the Sulbasutras mathematics, it got diffused on this region. And the other thing is that the Babylonian precedence hinges on the dates assigned to the Sulbasutras, and obviously we don't know, we will have to see, but the importance of the Sulbasutras was discussed in detail by Abraham Seidenberg in the article in 1962 and his other article in 1978. So there he states that the Sulbasutras have never taken the position in the history of mathematics that they deserve. And so he makes a very detailed study of Greek mathematics, Babylonian mathematics, and the Sulbasutras, and he comes to the conclusion that a common source for the Pythagorean and Vedic mathematics is to be sought either in the Vedic mathematics, that is the Sulbasutras, or in an older mathematics very much like it. So what was this older common source like? I think its mathematics was very much like what we see in the Sulbasutras. So why is it not the Sulbasutras themselves? If it is very common, if it is very similar to the Sulbasutras, the 2 points he mentions why why not the Sulbasutras themselves. One of them is the date of the Sulbasutras as 800 BCE, and the other one was the Aryan invasion theory. So in his article he states the Aryan invasion theory as a as a fact, and on the basis of this it becomes difficult for him to state that it is the Sulbasutras themselves which could have been the precursor of Greek geometry and Babylonian geometry. So both of these dates have to be both of these facts have to be investigated in detail to be able to judge this aspect further. So so I think that would be the end of my talk, and I hope I have been able to keep the time limit. Thank you very much.
Yeah. Thank you, Dr. Kamble. So now we open up the floor for any questions.
Well, maybe I'll start the ball rolling. Dr. Kamble, did you find this book any of any use, The Shape of Ancient Thought, Comparative Studies in Greek and Indian Philosophy by Thomas Machiavelli?
Yeah, I've heard of this book. I have not had the chance to read it though, but I really wanted to read it. But there he discusses several commonalities, right? The archaeological and historical and philosophical.
Yeah, that book came in 2001 and it created a storm in the US, and a lot of panels were created to discuss that book and so on. Yeah, in
Yes, yes,
philosophy and religious studies and philosophy. Yeah.
yes. It's a very important book. I have not had the chance to read it though, but actually, but even without that book, I came across several commonalities between India and Greece. Like even the philosophy of Socrates, his statements, his teachings, they are all very almost one-to-one correspondence with the Vedic and Hindu thought, as I have also discussed in detail in my book. The works of Pythagoras, and yeah, and also what you also also the writings of Seidenberg also show. Yeah.
I have two very small questions also. Two more. Do you see did you find anything ever anywhere that maybe the Jain thought of or Jain practice of non-violence might have also influenced Pythagoras? Did you ever see anything like that? Anything with Jainism and Pythagoras?
I saw, I think, more like this article by what was his name, von Schroeder, Pythagoras and the Indians. He spoke about Buddhist thought, but if I remember, I don't remember if he spoke about Jain thought specifically.
Okay, no problem.
But
And
obviously,
last one before, I think many others will have questions. So just quickly, last one.
yes.
Do you think the discovery of Rosetta Stone in Egypt might have helped locate their sort of, like you said, cradle of civilization, because they found that they could translate those languages, ancient languages, and we have nothing like that when it comes to Indian civilization or Indus Valley civilization? All right, that was the last question.
This I'm not in a position to answer. I have to look this up in more detail.
Okay, that's it. I'm sure many more intelligent questions are waiting for you.
Yeah, we have a question from Professor Maya Dot. She's asking, are you saying this case is not a one-off, and like the Black Athena, the history of mathematics needs a global retelling and rewriting?
Yes, sure. For sure, this is what I state, and in fact, there have been also certain articles in Nature and some others where more inclusive sort of history of mathematics was called for, appealed to, that the current history of mathematics is very Eurocentric and all those things. But the thing is that like here I see that most of them they state more like the case of the Arabic mathematics, Al-Khwarizmi, as the the non-Western things, and again the Indian contributions are again thrown out of the picture, because, and in fact when it comes to Al-Khwarizmi, his supposedly the creator of arithmetic and algebra is also in fact the fact is that they come also from the Indian civilization, arithmetic and algebra. In fact, I would love to also give a talk sometime on the the subject of algebra, how it arose in the Indian civilization, how it is connected to the Hindu thought. But yeah, so there. Absolutely. So coming back to your question, yes, but in a way which is like not in a way which is not like just not just by giving some credit to Al-Khwarizmi or Arabic or something, but the proper attributions have to be done to the Indian civilization. Yeah.
Okay. Do we have any more questions?
Yeah, people can just unmute themselves and ask the
Yeah.
question directly by unmuting them. Yeah.
Okay, then I will go ahead. So this is Amol.
Mhm.
Do you know whether there is any, whether there are any traces of connection of this Sulbasutra or any other methods that are discussed in any manuals or whatever around the construction of temples? Because I think in your opening slide you had shown the slopes of one of the temples somewhere and shown a
Yes.
right angle temple there. So there must be some documentation, hopefully, of how to construct temples. And maybe you can see that these methods are applied by those people.
Uh, uh, I mean, I have not come across specific texts on temple construction. So yeah, I mean, I would assume that they had access to the Sulbasutras texts, and it was part of their common knowledge amongst the artisans. I actually, more I cannot say, because I have not come across any specific text as such for temple construction, mathematical rules for them. So I think they were like
Because one of the,
yeah.
I was saying one of the advantages of some of the Western documentation is that
Hmm.
there are references and discussions of Pythagoras theorem in the documents by, I think, one of the famous Roman architects. I forget what his name was, but his architecture book is very, very famous and it mentions some of these things, including some things about how the theorems, there is no point, but the results they gave us are really useful, etc., etc. So I don't know if there is any comparable work in Indian architecture. I mean, the technology of the temples, not the other purposes.
I have not come across this actually. Are you mean to say any specific texts on temple construction?
As in the mathematics involved, right? Like you should draw a line from here to here with these proportions, then thus and so happens, and you can, get a origin, get I mean, for example, you can find these temples which are aligned to various solar phenomena, right? Like the light falls
Yeah.
over here on the equinoxes or what have you.
Yes,
But
yes, yes.
somewhere, maybe if we get lucky, there will be some document which actually records the technology, not just
Yeah, unfortunately, I
the
have not
final
come
result.
across those texts.
Can I
Yeah,
just jump in? Sorry.
yeah.
So actually, Dr. Kamble, this is an invitation for you to come to Pune. There's a
Mm-hmm.
museum of Vedic utensils, which was established. I mean, it's a collection that started about 100 years ago, and
Mm-hmm.
it's near the Tilak Maharashtra Vidyapith University. So the attempt was to find convergences between fire worshipping cultures. So
Mm-hmm.
specifically, they have a collection of Vedic utensils and also like yantras, right? How
Mm-hmm.
the Havan thing should be placed and all that.
Yeah,
And so I'm wondering, because of this sort of convergence between Babylonian and Vedic traditions, whether there is another history to also be uncovered, which is in the case of this collection, they're looking at the Avesta and the Vedic, points of commonality
yeah.
as textual traditions, really, right? So it is very textual, and of course, there's material objects also.
Mm-hmm.
But I wonder if there is, another kind of layer in between, which has to also do with practice. So I really appreciate Amod's comment, Dr. Amod Sani's comment, because I think the architectural practice, along with the theory, is what finally made its way into, temple architecture or
Yeah,
even worship. And this
absolutely.
fire worshipping thing became very central, right? To how to arrange, in what direction, all those questions. So the geometry
Mhm.
has a real life after. And
Yeah,
so, I think you would really love that space. So, please
yeah.
feel free.
Thank you so much. Yeah, thank you. Mm.
Are there any more questions? Okay. Dr. Kamble, yeah, I think we do have another question. Okay. Pranav is asking, you mentioned that some European mathematicians, scholars were
Mhm.
pushing a Babylonian origin for the so-called Pythagorean theorem because it fit their biblical narrative. Why
Mhm.
then did some of them push for an Egyptian origin earlier?
Uh, Actually, this was also like this was before because the Babylonian mathematics narrative became picked up in the 1920s because of the work of Neugebauer. But when Moritz Cantor was writing his works, he did not know much about Babylonian clay tablets and all that. He was aware more of the Egyptian tradition, and there he knew that they had this triangle 3 4 5. So there was some connection with Egypt. So this was the reason. And later on, when Babylonian mathematics became more famous due to the work of Neugebauer, it also fits in the biblical narrative of Babylonia, as the cradle of civilization. And even if you look at the word Mesopotamia, you don't hear the word Iraq said in the context. You always hear the word Mesopotamia. So this was a term which was revived, to sort of remove any connection with modern Iraq or that region. So right. So this is how I would think happened, the chain of events.
Right. Any more questions?
Also, just to complete the comment, I mean, Egypt plays a huge role in the Bible too, so it was a very familiar thing for.
Yes, especially the Old Testament. Absolutely correct. Yes.
Thank you.
So,
Yeah.
I was just wondering, I mean, this is a broader question of curriculum and probably pedagogy. Because we see there's this advanced mathematics that is being discussed in India. I was wondering, how was it taught? Like, did they have a similar system like we have now, where
Uh,
you have, yeah.
yeah. So of course, I think most of us are familiar with the traditional Gurukul system. So I think that was of course there. Yeah, where the students live at the ashram of their guru, and for a certain number of years. But there were also like higher educations of centers of education, like in Ujjain and other places. What I also found an interesting, information was there is this, if you there is this so-called Bell and Lancaster system of education, which was made famous in England in the 19th century or so. So when I was reading this book by Dharampal, Beautiful Tree, there he speaks about a temple, about one the letter by one Englishman, where he sees observes something going on in a temple, where he sees that the students are the older students are teaching the younger students in a sort of what is basically a self-correcting method of instruction, where the role of the instructor is minimized. And then he says that this is exactly the same as the Bell and Lancaster system of the education. So or the so-called Madras method, if you just look up on online on the so-called Madras method. So even in temples you can see that the education was imparted to students and things like that. So apart from that, I think for education, how it was done, I think the work of Dharampal would be a very nice resource. I'm sure many of you must have read that also. The Beautiful Tree, I think it's called, right? The Beautiful Tree. I have referred to it very extensively in my book.
Okay. Okay, Amod has a question. Yeah, please unmute yourself.
One interesting thing, by the way, is that I have wondered whether some of these Shulbasutra techniques could be brought back into use in schools. And I actually tried some things like this in a rough way, because
Mhm.
here is the idea. There is this discussion of collapsible compasses in Greek geometry. You probably have seen that, right? Like the Euclid's theorems are supposed to be provable with a collapsible compass, and you can't have measurement and so on.
Mhm.
So that whole collapsible compass thing never made any sense to me. But a rope does, because a rope fundamentally collapses, right? So I think this collapsible compass is some bizarre invention that was actually foisted on top of what was a rope-based foundation, because ropes do collapse. And it seems
Wow. Yeah.
fairly natural that given a rope, right, a triangle is easy to make, a circle is easy to make. So a rope is, and it's very, very cheap. You don't need to manufacture compass boxes and steel and all the other stuff. And you can just have ropes with small knots at reasonably regular distances. And that gives you your 3, 4, 5 triangle right away, right, without almost any effort.
Great.
So
Yeah.
technically speaking, you could reconstruct school geometry using ropes, and it will be far more efficient and more fun than all these compass boxes, because you can do it on a large scale on grounds and all, in especially rural areas and all. Because the thing about geometry, school geometry, that irritates me is that geometry, I don't think by its inventors was ever made to be about lines on paper, right? Lines on paper is a huge abstraction, especially in an era where paper was impossible
Exactly.
fundamentally.
Yeah.
So people must have been working on the soil, and a rope is a far more natural instrument on soil and what we carry around in the compass boxes. So anyway,
Yeah,
just
that's
side
actually
comment.
very, very interesting point. Yeah. Actually, what it also brings to mind, like how the so-called axiomatic approach of mathematics is, this philosopher, Arthur Schopenhauer, he once, like, he was very critical of Euclid's, the mathematics in Euclid, that is so axiomatic that, and then he was also in favor of something, a much more intuitive approach to mathematics. I just mentioned this point, because Schopenhauer's philosophy is very similar to the Upanishadic philosophy. So it's very interesting that he also makes the same sort of comments regarding axiomatic mathematics, what you were also pointing out with points and lines, right? And C.K. Raju also is very
And
much
especially
a
for
critic of this. Yeah.
And especially for children, the abstraction level is too high. Ropes are very
Yeah.
tangible and circles on the ground are extremely constructible.
Yeah.
In any case, you can see, for example, right? Oh, I'm sorry, I don't want to take over too much of this. It's your show, but just to make a point that, for example, in the old days, if you wanted to make like a castle moat, let's say, right, then the a rope makes a lot more sense, and you measure angles with ropes across a very large distance by just throwing the rope across instead of fiddling around. And then all these parallel postulates and measuring parallelism by looking at diagonal angles is an extremely practical thing. It is not just because on paper a child will ask, I can just see that it's parallel, right, more or less. But on a large distance across a castle moat, you cannot see that. You have to prove it.
Yes.
We also have two students, Ahana Srivastav and Yana Postwala. Any questions, Anna or Yana? These are students of Professor Renu Dadwal, just for information. Maya, they also came. And all right, I think that's it, Sanchari. Probably we can wrap it up. And you're most welcome to visit us at Flame. Do you ever come to Pune, Dr. Kamble?
Not for a long time. No, I had been to Bombay in February.
Okay. If you ever happen to, would like
Thank
to
you.
visit.
Yeah, I will. Yeah, I'll keep in mind for sure.
Thank you. Thank you.
Thank you so much. Yeah.
Thank you.
Bye.